Okay, so this is a 11th video in the series of name reactions, and today we will discuss Baker Venkataraman rearrangement. So I want you to try this reaction. So this is my starting material. In first step, I am using a strong base, sodium hydride, and in second step, I am using H2SO4 with water. So you may pause the video and try the reaction by yourself. So let's discuss the Baker Venkataraman rearrangement. So in this reaction, usually your starting material will look like this. So you will have a ester as one of your starting material part. And second, you will have this active methylene group. So this is how a starting material of Baker Venkataraman rearrangement looks like. And generally, the reagent uses simple base. So let me take one example of this kind with particular base and draw the mechanism and find out the product. So let's solve that type of reaction in next slide. Okay, so let me write the general reaction. So we have this ester molecule and we have this active methylene group, active methylene carbon. And let's say I'm using a base KOH. So this is what we call the Baker Venkataraman rearrangement. So we have a base, so we need to find out the acidic proton. So that's why this reaction needs active methylene group, because this active methylene carbon will have a acidic proton. So we have two hydrogens here. So my base can take this proton and can generate carb anion at this carbon. So we have generated a carboanion. Now this carbanion can go under resonance with this carbonyl, generating a enolate, right? So we have enolate here. So in this reaction, the intermediate is enolate. Now this oxygen can reform a double bond, and this enolate carbon can attack at this carbonyl carbon, opening up this bond. So this is a type of, you see, intramolecular reaction. So this will give me oxygen R1. Now this is O minus. This is again a carbonyl system. And now this carbon is bonded with this carbon. And this one has R2. Right? Now this oxygen will reform a double bond and will break this bond. So this will give me, and later this O minus will be protonated with hydrogen. So this will give me, so this has become OH. This bond is no more and this one has become OH. And here we have C double bond O. So let's number 1, 2, 3. So this is my 1, This is 2. 2 has R2. 3 is carbonyl, which has this R1. So this is the final product for this reaction. And if you look closely, we have converted this starting material under basic condition into this one. So somewhere we have hydrolyzed this ester and we have converted it into OH, and we have generated this 1,3-diketone system. And also, if you look closely, we have migrated this acyl group at this carbon. So this is what we call the Baker-Venkataraman rearrangement. It's just a base mediated reaction where you convert your ester into OH, and this whole acyl group will be migrated towards methylene carbon, and this is the mechanism for it. Okay, let's solve one question and draw the mechanism for it. So let's say this is my starting material and I'm reacting this with sodium hydride. So what product I'm going to get? So you may pause the video, draw the mechanism and find out the product. So sodium hydride is a strong base which gives me H minus. And we have hydrogen here, a active methylene carbon. So this hydride ion will grab this proton and will generate carb anion at this carbon. So this will give me C double bond O and a carb anion. This carbon ion can form enolate Now this enolate can attack at this carbonyl, opening up this bond. Right? So this oxygen reformed the double bond, and this double bond attacks from this carbon at this carbonyl, opening up this CO bond. Now this oxygen reforms a double bond and will break this particular bond, and this will give me the final product we are looking for. So this O minus will become OH, and here we have 1, 2, 3. So this is my 1. 2 has 1 methyl group and 3 is carbonyl with NET2. So this is the product for this reaction. So by looking at starting material, we knew that this is a Baker-Venkataraman rearrangement because we have an ester and we have this active methylene group present in the same system, and we have a base. And we did the intramolecular reaction, open up this ring and form the product. And we can see that we have hydrolyzed this ester into OH, and we have migrated this whole group at this methylene carbon right here. So this acyl group is now present here. Okay, so in the first slide, I have given you one question. So let's solve that one. So in first step, we have NaH, and we know we have this ester and active methylene group, we have NaH, so we know that first step is a Baker-Venkataraman rearrangement. So we have a hydrogen here and we have a base. So this base will grab this proton, will generate carb anion. This carb anion will attack at this electron deficient carbon, will open up this bond. So this has become O minus. This is still pH. We have a carbonyl. This CH2 is now bonded with this carbon and we have OBN right here. Now this oxygen will reform a double bond. This bond is going to break, and this is how we generate the product for first step, that is Baker-Venkataraman rearrangement. Okay, so this is the product for the first step. So we converted this ester into OH and migrated this whole group at this carbon, which we can see right here. Okay, in the second step, we have H plus ions coming from H2SO4. So we have plenty of H plus ions coming from H2SO4. This particular oxygen will take this proton and will get activated. Now this oxygen can also get activated, but let me write the product, then you will understand why this oxygen got protonated. So once this oxygen get protonated, this carbon will get activated. So this oxygen with its lone pair will attack at this carbonyl carbon and this bond is going to break. So this is the reason why this particular oxygen got protonated instead of this one, because in later part this oxygen will attack at this activated carbon. So this, if this attacks here, it will form 1, 2, 3, 4, 5, a 6-membered ring. But if this oxygen get protonated and this carbon get attacks, this will form 1, 2, 3, 4. So this will form a 4-membered ring, whereas this one is forming 6-membered ring. So that's why this 6-membered ring are more stable and it is preferred. So this gives me so let's number 1, 2, 3, 4, 5 and 6. Okay, so this oxygen is 1, 2, 3, 4 has carbonyl, and this fifth one has OBN. Sixth carbon has 1 pH and 1 OH, right? Now we have a hydrogen here, a acidic hydrogen here, because it is adjacent to this carbonyl. Now this can fall, eliminating OH. So water molecule is going to leave. We have OH and we have hydrogen, and double bond will form here. So the final product will be this one. So in the last step, we removed water, formed a double bond right here.